In this tutorial, we're going to learn how to calculate the average isotopic mass of an element. Now, you may notice that on the periodic table, the masses of elements are not given in whole number values. Rather, they're given in decimal units, which means that we don't have an exact number of protons and neutrons, as you may have thought. Well, that's because there is more than one version of a particular element, and that's called an isotope. An isotope is an atom of the same element, and therefore has the same number of protons, but therefore has different numbers of neutrons, which gives it a different atomic mass. So which of these isotopes would we have listed on the periodic table as the official mass for an element? For example, here we have boron 10 with a mass of 10.001294 and boron 11 with a mass of 11.00931. So which of these would we actually have on the periodic table? Well, the answer is neither. We would have to take an average to represent proportionally the masses of both of these isotopes. When we say average, we do not, and I repeat, do not just simply add the masses, in this case this value and this value, and divide by 2, because that's how we take an average. And if we had 3 isotopes, we would not take those 3 masses, add them together, and divide by 3, because that would not give us the correct average isotopic mass, because it would assume that all of these isotopes are equal in their abundance, and they're not. Notice here that we have what we call percentages of abundance that are listed here. What that means is that this is the percentage that naturally occurs on Earth of boron 10, that's 19.91%, and of boron 11, which is about 80.09%. So they're not equally weighted, so therefore we wouldn't find an average by just adding these numbers and dividing by 2, because that would make them equal, and they're certainly not. So what we have to do is take into consideration the differences in percentages of abundance, and therefore calculate the average mass so that it reflects boron 10 having a much lower abundance than boron 11. Basically what this means is that when we take the average mass that is reported on the periodic table should be closer to boron 11, because there is a lot more boron 11 in abundance than there is of boron 10. So our value should be somewhere between 10 and 11, but closer to 11 because of the abundance. So how do we solve these problems? It is very, very simple. So you shouldn't really miss these kinds of problems. First thing we need to do is convert all of our percentages to fractions, and of course we do that by dividing by 100 or moving our decimal over 2 places. What that means is that 19.91%, we'd move the decimal over 2 places to make it 0.1991, and there it is, 0.1991, and 80.09% would be moved over to 0.8009, and there we have 0.8009. Take the mass given of that isotope, this is boron 10, multiply by its fractional abundance, and you get the value that it will contribute to the average mass from this particular isotope. Boron 11 has a mass of 11.00931, as stated in the problem above, times its fractional abundance will give us 8.817. That is the mass that this boron 11 isotope will contribute towards the average isotopic mass. Take this value and this value, the parts that they contribute, add them together, and you get the average isotopic mass for this particular isotope, which is 10.81 atomic mass units. And that is the value you'll see reflected on the periodic table. Again, mass times fractional abundance gives you the part it contributes of the first isotope. Repeat for the second isotope, third, fourth, and so on if you have more. Add up the contributions of each isotope, here being this value and this value, and you will get the total, which is the value you will see on the periodic table as the correct average isotopic mass.